Welcome to Module 5 on Utah's Riverdale Road over I-84 precast substructure and its performance. We're pleased to welcome our speakers, Mike Arens, Vice President with Michael Baker International, and Mike Culmo, Chief Bridge Engineer with CHA Consulting, Inc. Mike?
All right, thanks, Mary Lou. Thanks everyone for joining us today, and thank you for the ABC UTC for organizing and putting these on. I think these are very important and very good presentations so far today to help us advance the substructure ABC technology. So as Mary Lou stated, today's presentation is on the Riverdale Road Bridge. The owner is the Utah Department of Transportation. Michael Baker International was the designer, and Granite Construction was the contractor, and it was contracted through the CMGC process, which Chris White talked about a little bit earlier, and I'll touch on the benefits of that here also with this project. So just a little bit of uniqueness with this presentation. So today we get the opportunity to go back in the time machine. This project was designed and constructed in 2008, so 15 years ago. And there were, two reasons for the accelerated bridge components of this project, both to accelerate the project, and I'll talk about the goals here a little bit, but also to try new innovative things out. This was 15 years ago. And so UDOT in their process has worked to follow up with their ABC projects and determine how they have been performing. And so that'll be the second part of today's presentation with Mike Culmo to talk about his work with UDOT in analyzing and looking at the performance here 15 years later of this project. So just an overall view of the project location. We're in Utah here. And this project in Riverdale, Utah was just north of Salt Lake City here in Utah. And an overview of the bridge here that has been constructed in place, which I'll be using the term SPUI here quite a bit through the presentation, which is a single point urban interchange where the ramps come in and converge in one lighting location in terms of the movement of traffic coming through the single point in the middle of the interchange, versus a diamond, which the ramps would come to here and you would have the two locations of the lights and the intersections on either side of the bridge. So the project goals for this project was to increase the interchange capacity. And so for that, the DOT, we upgraded the interchange configuration from an existing diamond to a SPUI. The existing bridge was deteriorating, so needed to replace that. We wanted accelerated construction to finish the construction in one season, and then we implemented ABC to minimize the traffic impacts to the public and the construction time to allow for that one season construction. So the existing bridge was a cast in place deck and girder bridge, and there was some decks falling and some cracking. So this type of bridge inherently is not a good type of bridge to widen and build off of. And where this new SPUI structure needed to be almost twice the deck area as the existing bridge to accommodate the traffic movements of a SPUI, it was considered for a little while to rehab the existing bridge and simply add to the width of the bridge to accommodate the SPUI. But we quickly determined that overall for performance and longevity to replace the overall existing bridge. So I wanted to sidetrack here just a little bit on the procurement method. So this project was executed using CMGC, and several of these projects have been discussed, have been alternative delivery, whether it was design build, CMGC, or extensive work with value engineering during the construction phase. But really, from an ABC standpoint, the benefits that a CMGC procurement method gets you is it allows the designer to work with the contractor right up front in terms of determining details, processes, innovations that will help the overall constructability of the project, and that the contractor will be able to implement without increasing risk, which equates to cost. So trying to avoid increased risks and costs with the project, and developing solutions that can be implemented by the contractor. Another big piece that the CMGC procurement allows for, and again, this has been touched on with prior presentations, is early material order, or early fabrication and execution of certain project elements. And so for this project in particular, the steel was far enough out that had we waited until final design was completed, we wouldn't have been able to get the steel in time for the girders and finish the construction in the one season that was mandated by the DOT. And so we were able to get enough of the design done to ensure that we could order the steel early, and the CMGC process allowed for that also. So back to the ABC, there's several parts of accelerated bridge construction that play into how we can build the bridges more quickly and minimize impacts to the public. And so, as we move forward here, we're going to focus on the precast bridge elements that we used in the substructure. But one of the other pieces is how the project is phased. And so for this particular project, where we were almost doubling the size of the bridge deck area to accommodate the spooey, we looked at how can we phase this project to keep traffic moving as much as possible. And our solution included using a full-size, oversized rectangular bridge shape versus the sometimes used hourglass shape with the steel girders that allow for either curved girders or tied in sections to create an hourglass shape, which minimizes the bridge area and accommodates the spooey movements. But in this particular example, we used the full-sized rectangular shape for the spooey. And what that did is that allowed us to build the outside quarters of the bridge while the diamond interchange and the spooey remained in service. And then we moved with temporary asphalt the traffic onto the outside quarters of the bridge, kept the diamond interchange in service while we built the inside half of the bridge, and then tied everything together, and with a short weekend closure in tying in all the ramps and connecting the signals, converted the diamond interchange into the operating spooey, and had it operating after the weekend for Monday morning use. And so the phasing was an important part of the minimizing impacts on this project. So with the substructure time, we had elements. We focused on high early strength cast in place footings on driven H piles. Then we had precast abutment segments and precast bent columns and caps on top of that, and then MSE wall panels tying into the abutments to accommodate the approach fills. So with the precast elements in general, one thing that was very helpful on this project was an on-site precasting yard. And so Granite was able to grade this yard out and have it close to the site, about a mile away. And what we also did with the precast yard is did match casting. So you can see here that the segments of the abutment were cast in place on top of each other as they would be in their final location. So when the segments were pulled off and taken to the final location and stacked back up for installation, everything went very smoothly and matched very well. And so the details here, we did use the cast in place high early strength pile caps as discussed in prior presentations, also just for a tolerance standpoint. We were able to the driving of the H piles does require quite a bit of tolerance if you're trying to put precast caps on top of those, and we felt we had the time to do the high early cast in place caps over those. And so then we allowed for a seat in the cast in place caps with shims, and then we placed the abutment sections in that and grouted those closed. What we also used that was a big piece of this, I think I've got that here, yeah, is the, we post-tensioned the precast elements together. And so this decision was made. There were a couple different reasons for that. Again, this was in 2008. This was early in a lot of development of standard details, of precast element details. And so as we were looking at the amount of mild reinforcement that would have to be spliced, the contractor was concerned with the tolerance levels and the amount of either sleeved splice connectors or threaded connectors that would have to be used to continue that mild reinforcement. And so between that and the seismic design considerations, we decided to go with post-tensioning rods, which high strength post-tensioning, which allowed us to reduce the number of reinforcement bars significantly. Now the seismic part of that was that we are in a high seismic zone here in Utah, and there was not research at the time, and really, you know, there's minimal research, or I mean, not fully accepted research right now, but with how grouted splices or splice of the bars perform in a plastic hinging manner. And so without having the ability to form our plastic hinges through the traditional, you know, ASTRO process or design procedure with the splices, we came to the conclusion that, again, at this time, back in 2008, that we decided to design this bridge for seismic forces elastically. And so I'll talk a little bit more about the bent forces when I get to the bent section, but what this did then too is the high strength rods allowed us to gain a lot of strength in the steel to handle the forces elastically as we did the analysis elastically. So we used epoxy layers between each of the sections, waterproofing behind the joints prior to backfilling them. And the one innovative thing that the contractor did come up with also, as these abutment sections were placed, it was difficult to try to align all of the high tension rods up at the same time to slide them through the sleeves as we placed them down. And so they essentially extended all of the rods with PVC at different lengths so that we could put the rods into the sleeves progressively as the abutment sections were lowered into place. So you can see here a cross section of the abutment piece, and we keyed in each of the joints, the grouted caps here at the top where we terminated the post-tension rods. And then this is a plan view of the abutment piece sections, which we had a little kind of fin wall, high cheek wall that came off of the end of the abutment, and the MSE wall panels then tucked in behind that to build up the approach fills with the MSE wall panels. So with the bents, a similar approach. We had high early cast in place footings on top of the driven piles with a embedment for the columns to be put into place. Let's see, and then the column sections were cast full height, so they were varied column heights for each location, and then the bent caps placed on top with 6 post-tensioning rods coming up from the foundation, 2 of them terminating at the top of the column to be able to secure the column in place, and then the remaining 4 extending up through the bent cap to secure it into place. We did go with octagonal shape columns, and that was a big reason was to accommodate the casting on the on-site precast yard. The contractor, where we had variable heights of the columns, they wanted to cast the columns horizontally to be able to have that tighter quality control of the lengths of the columns. But as you can think about it, if you're casting a column horizontally, it'd be tough to smoothly finish a full round column as you got to the top. So we incorporated the octagonal shape into the aesthetics, but really it was function over form in terms of the ability to cast them horizontally. So here's a detail of the column sitting into the cast in place footing cap, using shims to balance them up. And then once the post tension rods were threaded through the columns, the seat grouted closed to secure the seat, and then the grout tubes to the PVC to the sleeves to be able to pump the grout from the bottom up to the top to fill the grout post tension sleeves up with grout until they bubble up out of the top. You can also see even though we weren't using plastic hinging, we still detailed the confinement reinforcement both in the column and in the footing to be able to form the plastic hinge. And as noted on an earlier presentation, also we did not have continuous confinement obviously through this joint, but had the correct termination of the confinement reinforcement to allow for the plastic hinging per the AASHTO requirements. So transitioning here to the precast bent, this was by far the largest component of the precast elements. And even though we did have a close on-site precast yard for all the elements, the lifting and transporting of the cap would have been pretty restrictive in terms of the size of equipment, both the crane and the axle requirements needed to place these items, especially when we were working in the middle section of the bridge. When we were working on the inside, a lot of the precast pieces were delivered over the bridge on the new bridges and picked and set down into the middle. And so this weight would have really restricted the ability to do that. So we actually cast the bent caps, you can see here, in the median of the interstate that was going underneath this bridge. And so the bent caps were simply just picked straight up from their location and set on top of the columns. So to talk a little bit about the seismic design. So the way that we accommodated this bridge's seismic design elastically was we used PTF sliding bearings under the girders on the bent caps. And so during a seismic event, we designed elastically for the columns to handle the static brake force of the sliding bearings with quite a bit of factor of safety, kind of assuming that they might, if it's 40, 50, 60 years into the life of this bridge before it sees a seismic event, making sure that they could elastically handle enough force to break the PTF sliding bearing surfaces loose. And then once they were broke loose, the longitudinal forces were taken up by the abutments and the passive pressure behind them on each end of the structure. And then because this was such a wide bridge, the transverse forces were able to be accommodated by the large width of the abutments and the stiffness of the deck, transferring the transverse forces into the structure. So a cross section of the precast cap and the column underneath of it. This shows the two rods that we terminated at the top of the columns and tightened the columns down with the shims and the cap sitting on top of the columns, grouting that connection between them, and then the grout tubes down the footing, grouting the sleeves of the post-tension sleeves up through the top of the bent cap. So here's a couple of shots of the final bridge. Overall, I think it turned out with as many precast elements that were used, turned into a really good looking final bridge. As you can see here, we also had to incorporate an extension in the loading of the signal arm into the outside caps. We did leave all four bents separate, independent, versus trying to tie them together. And I felt that really accommodated quicker construction, especially when we were in the middle section of the bridge. So a few of the lessons learned. The match casting worked very well. It was just, it worked very nicely to have everything fit together and know that we weren't going to have to do a lot of shimming to get everything to work. Allow for plenty of precast time up front, even though we got the precast going ahead of time. Just learning the process and working out some issues and tweaks in the precast yard ended up kind of bumping the precast time up very closely to when they were waiting for the pieces out in the field. So just make sure you've got the time there in that area of the project, so leave plenty of time there. And then coordinating the accelerated bridge construction with the overall schedule. And this was more of a project specific item, but we had to incorporate some lightweight fill behind the MSE walls. And with the phasing of the traffic, we did end up with some of the bridge being ready to be constructed more quickly than the road was ready to accept it. And so just thinking about the other components of the connecting to the bridge just outside the bridge construction itself is an important part of maximizing the ABC schedule benefits. So with that, we'll turn it over to Mike Culmo to talk about the long-term performance.
Thank you. Okay, it's a pleasure to be here to talk about the performance of the Riverdale Road Bridge. This is a structure I visited actually 7 times over the last since 2009. So we'll talk about how well this bridge is performing over time. Utah DOT does a series of, they're big into lessons learned. When they try something, especially something new, they look at how things perform and what we can learn moving forward to do future projects. So the goal was to study the performance of common ABC details across the state, and not just the Riverdale Road Bridge. We looked at a number, actually 50 bridges. We've done inspections out there starting in 2009 through this year, 2023. A total of 7 inspections have been completed, looking at 50 bridges each time approximately. The Riverdale Road Bridge has been inspected all 7 times. So I jokingly think maybe I've been at the bridge more than you have, Mike, but I've been out there many times, and I have to say this is one of my favorite bridges that we look at in the Utah inventory. So the ABC technologies that we study throughout the entire program, we look at SPMT, lateral slide, we look at a lot of precast decks with various types of connections, and we do also look at substructures. So overview of the findings. Almost all the details we look at are performing very well. We see very few problems with these ABC bridges. As I mentioned in my first presentation today, we try to emulate cast in place, and people always ask about durability, and really all we're doing is replacing construction joints with joints between precast elements, and they are all performing very well. There were some details that didn't function well, like the welded tab connection for deck panels. Did not work very well, but we have to understand that when Utah DOT built these bridges in 2008, there was no national specifications. There were no standard details. I talked in my first presentation about the 3-legged stool. All 3 legs were missing at that point. So engineers in Utah, including Mike and his team, were working basically using engineering judgment. They did a wonderful job on this bridge, but other details in Utah have had problems, and they're no longer in use. The issues that we've uncovered are not always related to ABC. And you'll see this bridge is a good example too. There's certain things that we see going wrong, but there's also things that we see going wrong with other bridges that are not ABC bridges. So we need to be careful to separate out issues we see during these inspections. Are they ABC related, or are they just related to other factors, such as just the general detailing of other features of the bridge? So we take a careful look at that every time we do these inspections to separate out what can we do better with ABC versus what may be an issue with, say, approach slabs, is a good example. So the performance of Riverdale, the key thing we're going to focus on today is the substructures, the precast abutment and precast pier that Mike just spoke about. There's also a precast deck, and there's other features in this bridge that we look at every time, but really today I'm just going to focus on these 2 major elements. So as far as the pier, as Mike showed, it's connected with vertical post-tensioning rods. It's performing excellent. There's virtually nothing wrong with this pier. After 14 years, 15 years in service, there's no issues at all with this pier whatsoever. So here are some photos. They're just from the 7 inspections. They just grabbed a few. And if you look at these photos, you might say they all look the same, and that's because nothing really is changing. The pier is performing wonderfully. There's no issues noted. It looks the same in 2023 as it did in 2013 and even 2009. So performance is just top notch, as good as you can expect. As good as you can hope for, I should say. The abutment is also vertically post-tension, as Mike showed. Same thing, there was no issues noted. He mentioned how the waterproofing was done behind the abutment. At the joints, we see no signs of leakage coming through those joints at all, performing very well. You notice the artwork on the abutments. Utah does a lot of artwork on their bridges. I'm not sure if Mike, if you were you posed for the fisherman in the middle, but the artwork is holding up well. But really, as far as performance of the abutment, there's no issues whatsoever. There are some issues with the approach slabs, and this is a good example of issues that may or may not be ABC related. The joints on the bridge with the approach slab met the end of the deck. There were issues fairly early. In 2016, the joint was starting to require some maintenance, and by 2023, the joint had to be replaced. We've seen a lot of issues with approach slabs in Utah, but we've also seen the same issues with cast in place approach slabs. So this is a good example of a detail performance issue that may not be related to ABC, may be related to other things. So, but a minor issue with the bridge that had to be repaired, and this is after 15 years of service. Again, at Utah DOT, we are looking at other potential details for approach slabs to try to minimize this sort of problem in the future. So these are kind of related. We found a couple minor spalls in the corners of the bridge where the approach slab meets the end of the beam. A little spall there. It might have been a little bit of construction where the gap might not have been large enough to accommodate the settlement of the approach fill. Minor issue that has since been repaired. Really minor stuff. So in conclusion, the Riverdale Road Bridge, I think is a great example of a total precast solution. There is a lot of precast on this bridge. There's very little cast in place, and sidewalks and barriers, I think, are probably the only major features that are cast in place. The substructures are performing very well. There are really no issues at all. Minor issues with the approach slabs that have been addressed or are being addressed. But I can honestly say, especially with this particular bridge, the service life of this bridge with the precast substructure should be equivalent to or greater than a conventional bridge built with cast in place construction. So performance is excellent. Looking at all the other bridges that we look at, the 50 bridges in the inventory, things like post-tension deck panels work very well. Lateral slide bridges are fine. SPMT installs are fine. So in general, the ABC methods used in Utah are performing very well across the board. And the key thing is that all the details that are in the AASHTO guide specification for ABC, all those details that are being in use in Utah are also performing well as well. So part of the goal of building the ABC guide spec was we measured the durability of every detail that went into that spec to make sure that it was equal to or better than conventional construction. And what we see in Utah is playing out, that the performance is very good on all these bridges. So with that, that concludes our presentation. We'll be happy to answer any questions.
Thank you, Mike and Mike, and great news on the performance. Utah just remains the leader in our ABC work. That's wonderful. We'll now begin the Q&A session. Paul?
Yeah, thank you, Mary Lou. Mike and Mike, really interesting, and we do have a few questions. We have a couple that came in during your talk. I'll ask one of them right now, and it was lightweight aggregate considered to reduce the weight of the bent caps?
Well, I'm going to have to remember 15 years ago here, but I think that that was, UDOT has used quite a bit of lightweight aggregate in some later projects for a while, but in this particular case, we didn't consider it on this project now.
Okay.
I'll add, there are several bridges, one particular in Salt Lake City, where it was an SPMT install, and they use lightweight concrete for the deck and the parapets to reduce the weight to minimize the size of the SPMT. So it has been, they have used some lightweight, but predominantly we're seeing normal weight concrete.
Okay. We have a question here, and not so much this bridge, but any of the other bridges you've had in Utah, I was thinking, and Mike, or anywhere else you've seen it, is galvanic corrosion with black steel and galvanized corrugated metal pipe sleeves an issue that has been encountered anywhere?
We haven't seen that as an issue, although a lot of states are moving to coated reinforcing bars and substructures as well as decks. It's becoming more and more common. We're seeing more galvanized bars and substructures, and I think in New York City they're using stainless steel bars and substructures. It hasn't been brought up as an issue, although we have in the industry, it's not that uncommon to mix galvanized bars with pre-stressing strands and girders. We've seen that done too. It doesn't seem to be that big a problem. I think on paper it potentially could be a problem, but it hasn't manifested itself in issues in the field. The key thing is with these galvanized sleeves, and that's another thing too. Galvanized sleeves are commonly used in post-tension construction. Most post-tension ducts are galvanized steel. It just hasn't manifested itself as issues in the field. If you think about a typical post-tensioning structure, has got an uncoated strand inside of a corrugated metal tube that's grouted. I don't think there's an industry issue with that particular combination.
Okay. This is a pre-webinar question here about, has the use of precast substructures proven to decrease or increase the lifetime performance of the structure?
I guess that question is in my court. I like I said on my final conclusion, it's on the screen or was on the screen, is I can very confidently state it's at least equal to, if not better. And one of the reasons I think it's better is when you do say an abutment, you do a cast in place cantilever abutment, when you pour the footing and then you pour the stem, even though we put construction joints and contraction joints and expansion joints in the abutment, it's very common to get shrinkage cracks and abutments, vertical cracks. As the concrete stem shrinks, the footing restrains it, we get restraint cracking. One of the great things about precast construction is you don't have restraint cracking because each individual element is allowed to shrink on its own while it's curing without the constraint of the adjacent elements. So you get these structures, literally, you cannot find cracks in these structures. Now, I think we could all agree that having a structure that is crack-free has nothing but positive impact to the future durability of the structure.
Okay. Another question came in earlier was, compared to the cast-in-place approach, what are the costs of precast substructure?
Yeah, I guess that ball's in my court. We didn't talk much about cost in this presentation. I referenced this morning or earlier today about the NCHRP Project 12-102A training modules that are available on the NCHRP website. There is a session on costing. But one thing I do talk about always when it comes to precast, and Mike's example is a great example where the contractor chose to precast adjacent to the bridge if they could. And if you are precasting, say, in a plant, the material is handled multiple times. In a normal cast in place construction, you handle the concrete once. It goes from the batch plant into the form. In a precast operation, it goes from the batch plant into the form. Then it goes from the form and it's stacked. It goes from stacked on a truck. It goes from a truck and gets delivered to the site. So you're handling the material 4 times. Every time you go to pick up a piece of precast, there's a cost associated with that. So it's hard for precast to become cheaper than cast in place. But there is one situation where I think it is, and in Texas this has been proven out, when it comes to bent caps. Casting a bent cap at 30, 40 feet in the air is an expensive operation. You're working at elevation, you're casting at elevation. Contractors have told us casting a bent cap on the ground and installing it quickly is probably cheaper than cast in place construction.
Okay. Here's the questions. A little came in during the presentation, but it was talking about the use of geofoam material. You talked about settlement at the indents, and I just wondered if y'all had any experience using that material to either decrease the load or maybe the settlement, decrease the load of the infills.
Yeah. So we've used geofoam on several of our bridge designs out here in Utah. And because we have the soft lake bed soils, you have issues with short-term and long-term settlement impacts to utilities. and global stability of the areas also if you put too much loading on them. And so the geofoam is a great solution. For this particular bridge, it was kind of in that middle zone where the lightweight fill reduced the loading enough that that it handled all those problems, and we didn't need the geofoam, because geofoam is another step up in expense from the lightweight fill. But both of those are great solutions, and we've used geofoam on a lot of bridges out here in Utah.
Okay. Were you using it 15 years ago, or was this? Okay.
Yeah.
All right.
Yeah.
You got a history on it.
Well,
Okay.
it's interesting, Paul. The ASHTO ABC guide spec does include provisions for geofoam because it is a rapid way of building an embankment, an approach embankment as well. It's got structural benefits, but it also has speed benefits as well. So we included that in the ASHTO guide spec as well.
Okay. We're just about out of time. I'm going to ask Rick if we've got any more questions that have come in, and he'll try and.
So there's, yep. Yeah, there's one here. What was the issue with the waterproofing membrane and the AC? Was that on the substructure to the approach or something? Was there some reference to that?
Oh, well, so we used waterproofing membrane behind each of the joints for the precast segments for the abutment. So that we wouldn't get, effervescence or just, drainage coming through those, that both from a performance standpoint, but really from an aesthetic standpoint too. And as Mike kind of referenced in the pictures, the abutments are still very, clean and new looking also. And so that's where we use that waterproofing membrane behind each of the precast joints.
Yeah, it worked perfectly. Those abutments look like they're brand new, and it work.
Yeah. Well, especially with the artwork, you wouldn't want stuff coming through or something else, right?
Coming through, right? Yeah.
So there was one reference here, one question about a comparison of time, and I don't know when you guys first looked at this project, if it was just done as a cast in place versus the precast that you ended up doing. Was there, I know you can always theorize what the savings in time was on it, but I'm assuming there was some question about that at some point.
Yes, and I think what we calculated was, right around that 4-month time frame, but then it also, that 4 months kind of kicks you over through the winter construction season, which, either you add costs with concrete heating and all the risks that come with that, or you hit the pause button for a couple months, which turns the 4 months into, 6 or 7 months. The other thing, though, that the precast definitely helped accommodate here was the way that we did phase the bridge from the outside in. Obviously, when we built the outside phases, the contractor had pretty easy access to do that work. But once we transitioned to the inside phase, building inside of those active bridges, having to form up abutments, form up bends, cast the concrete in that middle phase would have been more expensive and complicated, and possibly more impacts to the traffic, versus having the precast elements made that construction of the inside phase go more quickly and more cleanly and less impacts to the traffic. So the phasing, or the ABC accommodated the phasing portion of this also.
Yep. So a major issue with ABC is just minimizing the impact of traffic and accelerating the project forward, and that sounds like that did exactly what it wanted to. So I guess with that, we're out of time on this module, and we'll turn it back over to Mary Lou.
Thank you all.
Thank you, Paul and Rick. We're now at the end of the 5th 40-minute module. Thanks again to Mike Arens and Mike Culmo for presenting the 5th module.